Good afternoon, good evening, and good morning, everybody, and welcome to our today's new podcast about fast steering mirrors for free space optical communication. And I'm very happy to host this session today with Jochen Geiser, who's Marketing Strategy Manager, especially in this topic. He's our today's expert. Jochen, please introduce yourself.
Hey Mark, thanks for having me. My name is Jochen Geiser. I'm with PI since more than 4 years now. I started as a technical sales engineer. In this role, I supported our sales team, especially during the pre-sales phase, as a technical consultant. So in this time, I learned a lot about our products and our technologies, but also especially about our customers' applications. And since February 2026, so only a couple of months now, I'm working as a marketing strategy manager. In this role, I can leverage the know-how I gained as a technical sales engineer. So the role is really about making complex technology understandable and actionable for our sales team and our customer. So it's really about translating technical requirements, technical capabilities into customer value and value proposition. So in short, I'm connecting the dots between application, technology, and customer value.
Perfect. Thanks, Jochen. And today we will learn something very interesting about the positioning task in the free space optical communication applications. But let's start first with let's say, in the description of the challenges of this application. And therefore, I guess the viewers are very interested in what kind of applications are we speaking about?
Yeah. So the most of the application we're working on are located in the low Earth orbit. So the low Earth orbit is the region in space which is about 200 to 2,000 kilometers in altitude. So it's the region where most of today's applications happen. So it's a workhorse region in space. And in this region, we have different applications. So the major application is probably communication. So we have huge satellite constellations which provide global internet coverage. On the other hand, we have applications for Earth observation. So it's about tracking climate change, monitoring weather, but also about managing natural disasters like wildfires, or even supporting agriculture with analyzing land use. Further, we have applications for research, like the International Space Station, where experiments take place. And last but not least, we also have to discuss space debris. So due to the fact that there are so many satellites in space, we also have space trash, and we have to think about a removal. So it's the fourth important application, and these are the applications which take place in the low Earth orbit and which need a communication between the satellites, but also between satellite and the ground.
And that's for our today's topic, right? The communication between satellites, ground stations, but especially between satellites, the satellite-to-satellite communication. How do we bring our solution in such an application? Well, let's start with the application stuff. How does the communication between satellite to satellite work?
That's a good question. So when we want to understand how this works, we first have to understand how this communication takes place. So instead of typical radio frequency, which most of us know from a radio, for example, we're using laser-based communication. So we use light to transfer data from a satellite to a satellite. So, and to do this, these satellites have to find each other. So you have to imagine these satellites, they move with 7 to 8 kilometers per second, and they have distance of couple hundred to a few thousand kilometers between each other.
Okay.
So we have to establish a link between satellites to enable the communication between the satellites. And for this, we need typically 3 steps. First, we need a pointing. This means that 2 satellites which connect to each other, get a signal that they have to connect, and where are they located in space. So they get the GPS information and they start a course pointing towards the other satellite. And due to the fact that they are so far away from each other, we have to point really accurate. But that's the first step, the pointing. So you're trying to focus on the satellite, which is you want to build a connection with. And in the second step, the so-called acquisition step, they start to optimize the link by aligning their communication terminals to each other. And they this is an optimization process during this acquisition phase until the link is stabilized and the link is good enough to transfer the data in the required data rate. And as soon as the link is established, the third step takes place, which is called the tracking. So during the tracking phase, we stabilize the link by compensating all disturbances. So that's the way how these satellites communicate with each other, laser-based communication.
With that distance in between.
With this distance in between, exactly.
That sounds very crazy. So it's about pointing, acquisition, and tracking.
Exactly.
To find the right link between both of those satellites.
Yeah.
Wow.
And from a motion perspective, first we need a really huge motion with less frequency. And the more established the link gets, the more it is about fine correction or fine compensation with higher dynamics, but shorter travel.
Yeah. That's sounds very unreal to me, but to have a better picture, and I guess for the viewers, you have a slide prepared for that to describe how does the link or this pointing and acquisition and tracking work in this application. And I guess we can show the slide and you can explain how does it work. I mean, and where is our solution in that?
Yeah, so I brought a slide, as I already mentioned, and we see such terminal, which is often called a transceiver, because they send and they receive signals. So we use them for both. First, we have a look at receiving a signal. So the signal or the beam is steered onto the receiving satellite, and first is reflected by a cos pointing mirror. So the task of this is a coarse alignment of the beam or of the link between the satellites, and is then steered to a second mirror, which is typically a fast steering mirror. And the task of this fast steering mirror is the compensation of high frequency disturbances like vibrations and stuff like that. So it's about the fine motion and the fine compensation of the beam. The beam is then reflected on this fast steering mirror towards or typically to a beam splitter where the signal is divided between the incoming and outgoing signal, and is then processed inside of the satellite. This means the signal is demultiplexed and demodularized, and the data is processed. When we have a look, or what we have to consider to establish this link during sending, the satellite which sends the signal always have to align the signal again. So when a satellite receives a signal, he always sends a beacon, which is a reference signal. For constantly aligning the signal. So when we have a look at the outgoing signal, we have a laser source, which is then, or the lasers modulated and hits on a point ahead mirror. So this point ahead mirror makes a compensation of the relative velocity. So even the signal is transferred via light, which is incredibly fast, we still have a delay due to the fact that these
the travel of speed, light. I mean,
that these satellites are so far from each other. So we have to point ahead of the satellite to hit it. And so in the outgoing beam, we also have an additional point ahead mirror, which compensates this.
So we're focusing close ahead or in front of the satellite.
Exactly.
Of its way.
Exactly.
Okay.
So and then the signal goes back into the receiving path, which means first on the fasting mirror for the fine positioning, and then on the coarse mirror.
But with that precision and that travel range of the signal, and you mentioned the precision, and we have a lot of disturbances by the environment and the conditions we are facing in a satellite, right? I mean, what are the major challenges we are facing when we are bringing our solution, our products in such a satellite? What is the major topic we are confronted with?
Yeah, we have a couple.
A couple
Because
of it.
it's so
Not only
it's,
one, not
yeah,
only
it's,
vibrating.
it's a really rough
Okay.
environment. So so this slide we saw, so it's just to mention, it's just a general overview, which it's not the design everyone uses, but it gives an idea how such a system is built. But when we are in space, we first have to get things in space. So we have to be rocketized. Things has to survive a launch of a rocket, so
Okay.
it needs to be vibration and shock resistant. So robustness is really important.
Mhm.
Then, of course, due to the fact that the satellites are so far away from each other, we need a really good pointing accuracy. So accuracy and stability of the position is really important, because we need to steer this narrow laser onto the satellite, which is so far away. So accuracy is really important, typically in the microradian, rather sub-microradian range. We need high dynamics, because everything is moving so fast. We have to compensate all disturbances almost in real time. Further, we have to think about the environment in space. So we have radiation and we have a vacuum. Everything has to be vacuum proofed. So we have to ensure that nothing is outgassing, that we do not have any gases condensing on optical components, which could have a bad impact on the link, or in worst case lead to a failure. And in addition, we have to think about thermal stability, because these satellites, they see sunlight and shadow in a high frequency, so everything is heating up and cooling down. So we need a thermal stable system. And last but not least, everything has to be reliable. You have to think about these satellites typically cannot be maintained, so they have to work a couple of years, and we need a maintenance-free, robust system.
Exactly.
For long
So
lifetime.
a tough, robust, shock vibrating and vibrating resistant, high precision, thermal resistant, not outgassing in vacuum. It's
Exactly.
a crazy list of environmental conditions and challenges there. But I guess we have some solutions.
Yeah, we do. Absolutely.
Perfect.
Yeah, it's just we already have a couple of thousand fast mirrors in space.
Really?
From different technologies. So we have a voice coil-based product, but
So this is real. We have a lot of
we have a lot of opportunities and a lot of solutions. So, and we have to imagine. So basically, we have two different techniques. We have voice coil-based fasting mirrors, and with feeds-based fasting mirrors. Voice coil-based fasting mirrors have the advantage that they offer a larger travel, however, with a lower dynamic than RPA solutions. And as of today, we have customers who buy our standard products and send them to space, and they work really fine. And on the other hand, we have customers...
Perfect, when it's fitting right from the shelf, right?
Exactly. And on the other hand, we have customers who get a highly customized product, which fits perfect into their application. So, but when we go back to setup of this transceiver, of this phase-based optical communication terminal, we saw that we have three different tasks. So the coarse, the fine positioning, and
so three mirrors in most
typically,
of the...
Typically three mirrors. Sometimes, the design differs, but these have different requirements. These mirrors, but there are customers who are saying they want to have the same product for all these tasks. But we have customers who have different solutions for these different tasks. So, and that's why we also have different solutions which are requested by our customers, because it always depends what of these high precision motion is done by our products.
So, but when I'm the customer and I'm looking on a product I'm not finding on our, let's say, on PI standard product portfolio, how can I, or how do we work together? How does it work when I have some really tough environment, all this rough requirements? So how do we work together in that case?
So when we do not have a solution off the shelf, it's not the end of the story. It's typically exactly the point.
It's the
where
start of the next story,
where
right?
innovation starts.
Yeah.
Yeah. So we want to we want to have the discussion as soon as possible. So we're always happy if we can be a partner for our customers as early as possible.
Yeah.
Because we have different technologies which have different advantages. So we want to understand what is the application about. We want to understand what are the requirements,
goals.
the performance goals.
Yeah.
What are the budget? What's the ramp up? So it's a complex environment. We have to consider more than just performance of one motion system. We want to understand, if possible, we want to understand as much as possible to provide the best solution for the customer, which means the solution is good enough. So it works perfect in the application, but it's not over-engineered. And to provide our customers with a good enough solution, it's always the best to
the
start
sweet spot of everything, right?
Yeah.
The budget, the performance, the engineering, everything. So sweet spot of everything.
Yeah, exactly. So and to find the sweet spot, it's typically the best to start the discussion as early as possible, and to consider all different solutions we're having. Yeah, so we typically start with a requirements engineering, where we want to understand what is what's the motion about. So we want to understand what kind of motion does the customer wants to do, and what does he need, and then make a technology agnostic approach to do not be focused on one technology, but on finding the best solution for the customer. Yeah, so it's we have discussion, make
so including us in a very early stage in concept phase, feasibility studies. So we are our expertise is to support in precision moving objects and manipulating objects in the room, right? So including us in a very early stage is a benefit for, let's say, everyone, and we learn from each other, from our customers, from our applications, also for the next gen of our next products, but not finding or having the solution in our shelf. We invite you guys out there, include us in your next applications, in your ideas, and we are listening. We're listening to your requirements, and we will find together the solution. So, Jochen, wow, very interesting topic today, and thanks for being with me and sharing all this information.
Okay. Thanks for having me.
Okay,
It was a pleasure.
Please visit our website and contact us with your next application. We're very happy to support you and looking forward for the next session. Thanks, Jochen.